Hey, Algebra 2 honor students, this is going to be Unit 7, Day 6, and today we're talking about how to solve systems of equations. Now, in this unit, we're looking at quadratics, right? That's our main topic in Unit 7 here, and you can see that if you look at the two equations that were given in number 1 here, the first one is quadratic. It's going to have an x squared term in it, but the other one's not. So what we're thinking of here is we have a system of equations where we have a parabola, and then this is a linear function. And if we think about how many solutions we could expect when a line intersects a parabola, well, there could be as many as 2. Maybe the line will hit the parabola twice. There are some special circumstances where maybe it would just kind of like glance off the side of the parabola. Maybe there's only one solution. And of course, there's the case where maybe there are no solutions at all. So we want to try and analyze today, how many solutions should we expect, and how can we determine the solutions in the end? So for this first example, I think it's actually nicely set up to talk about the process of substitution. Here I have y equals, so y is in terms of x already. And what we can do is, since the other equation is not explicitly solved in terms of y equals, we can replace this y with the quantity 1/4 x minus 3 squared. So if I make that substitution into this equation, then that would allow me to solve the system for x. When I solve the equation for x, I'll then go ahead and plug it back in for y. So let's go ahead and make that quick substitution. We get 3x minus 2 times y. So y is 1/4 of x minus 3 squared. And that equals 13 on this side. So what we want to do is we want to just kind of keep simplifying algebraically here. If I just kind of multiply the -2 times the 1/4, we get 3x minus 1/2 of x minus 3 squared is equal to 13. And maybe in the next stage, we're going to start breaking this apart and think about squaring the x minus 3. So we get 3x minus 1/2 times, that's going to become x squared. Think about box method or FOIL, you're going to get a minus 6x in the middle and then a plus 9 from that result. Now, by the way, if that 3x wasn't there, I probably would have multiplied both sides by -2 to get rid of this -1/2 and square root. But I know that I'm going to eventually have to combine like terms with the 3x and then this term in the middle here. But before I even do that, I don't love when I have to deal with fractional coefficients. And that's exactly what's going to happen if I distribute a -1/2. You're going to get -1/2 x squared. You're also going to get a -9/2 at the end here. So although this is not a completely necessary step, I think it's nice to do it just because it will make your values easier to work with. I'm going to multiply both sides by 2 because that would just make this a -1 out front then. And I think it just makes the values a little bit easier to work with. Okay, so just make sure you change everything appropriately. Now it's 6x minus 1 times x squared minus 6x plus 9. And on the other side, you have 26. So now at this point, I'll distribute that negative in to get -x squared plus 6x minus 9 equals 26. And now the whole goal is let's kind of clean some things up, move things to the other side. You know, if I add x squared to this side, because I like factoring with positive x squared, and that's where we're headed with this. I'm going to add x squared over. This is a total of 12x. So that's going to get moved over here to become -12x. And finally, if you add the 9 over, you get a plus 35 equals 0, right? Add the 9 to the 26. Okay, so that was, a couple different algebraic steps that we took there, but now we have a quadratic in standard form set to 0. How many different ways can we solve a quadratic set to 0? 3. We can factor, we can use quadratic formula, we can use complete the square. Out of those options, certainly factoring would be the fastest if it's available to us, and it happens to be. We get x minus 5 and x minus 7 are the factors here, right? Those multiply to positive 35 and add to -12. Therefore, we get x equals 5 and we get x equals 7. Perfect. Easy enough, right? Except we're not really done. Okay. Why are we not done? Well, remember, the solution to a system of equations is really the points of intersection. We found the x values for these points of intersection. What we haven't found is the y values that go with them. So at this stage, you now have to go back and plug these values of x back in to either of the original, doesn't matter which one, to get the y values. So if I use the, I don't know, I'll use the linear function. Usually that's easier, not always, but 3 times 5 minus 2y is equal to 13. So that's going to be 15. So if you subtract the 15 to the side, that becomes negative 2. And therefore y equals 1. So one solution will be 5 comma 1. I'll write that down in a moment. If I do the same thing with the 7, 3 times 7 minus 2y is equal to 13. So we get negative 2y equals, let's see, if I take 21, subtract it to the other side, that's negative 8. So now we get y equals positive 4. So in the end, to write our solutions, plural, we have the 0.51 is a point of intersection, and also the 0.74. So this is a process that you certainly would have done in Algebra 1, solving systems of equations. Certainly in Algebra 2, you're going to see that some of the steps that we take algebraically to simplify are going to be a little bit more complex looking, depending on the scenario. But once you get those two values of x, it's very easy to stop there and for students to say, yep, got it, got my two answers. But it's important to remember what we're looking for is these coordinate points where the two graphs intersect. So that those are the solutions to number 1. Let's take a look at another example. If I gave you the system of equations, 2y minus 3 is equal to x. That's not what I wanted to write, guys. Sorry, we'll try that again. All right, pretend that never happened. I wanted to write 2x minus y is equal to 3. I don't know where I got that from. I completely rearranged all the variables and numbers in my head. All right, and then I want y plus 6 is equal to 2 times x plus 1 squared. Okay, so we're going to solve the system in a moment. I want to compare it to the system that we just solved. And remember when I started this one, I said, hey, this is y in terms of x. So we can really easily sub into the other equation for y, this expression that has all x's in it. Well, that's not necessarily the case for this example here, is it? Right? I guess I could easily get one as y in terms of x. But what I'm going to wind up doing for this one, which is also a possibility algebraically, and this might make your life pretty easy, is I'm going to get both in terms of y. So if you do a little rearranging here, I don't know if that's what I was trying to do in my head when I wrote it originally. If you do some rearranging, you get y equals 2x minus 3, right? Add the y here, subtract the 3 there, something like that. And then this one, all you have to do is subtract 6 to the other side. So we get y equals 2 times x plus 1 squared with a minus 6 after it. Because if you set them both equal to y, then to solve the system, if y equals this and y equals that, then these two things are equal. Okay, so we're going to set the quadratic to x plus 1 squared minus 6 equal to 2x minus 3, and then solve from there. Okay, so we have a little bit of algebra to go. Make sure you square this before distributing the 2, right? We got to do some PEMDAS. And of course, you would never distribute the square ever again into a binomial. We've talked about that a lot, how that's not good algebra, right? Okay, so that becomes x squared plus 2x plus 1. Maybe now I'll distribute the 2 in to get 2x squared plus 4x plus 2 minus 6 equals 2x minus 3. I can combine these as like terms to get 2x squared plus 4x and a minus 4 at the end equals 2x minus 3. Okay, before you go to solve a quadratic, it has to be set to 0. So don't try and factor anything yet, or don't like take out a GCF of 2. Let's move these terms over to the other side and see what happens. So if I subtract 2x over, now the middle term is positive 2x. And if I add the 3 over, I get minus 1 is equal to 0. So now at this stage, I can ask myself, like, is this factorable? And I can try some box method off to the side. I can do some slip, divide, slide if you like that technique. You'll find pretty quickly from trying some different possible combinations that it turns out this is not factorable. And when something's not factorable, we have other strategies. We can use complete the square or quadratic formula. I would tend to use quadratic formula in something like this so that I don't have to worry about dividing out the 2 as the lead coefficient and getting an odd b value, and there's a lot of fractions that result from that. So let's go ahead and use quadratic formula, which would be x equals negative b. So that's going to be negative 2 plus or minus the square root of b squared, so 2 squared, minus 4ac, a is 2, c is -1, all over 2a, just don't forget a is 2. Okay, so then if I simplify, x equals -2 plus or minus the square root of, that's going to be 4 and then plus 8 under the radical, maybe? Yep. So 4 plus 8 is a total of 12, and that's all over 4. Square root of 12 can be simplified. It's the same thing as 2 radical 3 all over 4. And in the last step, you can reduce these coefficients a little bit further, can't you, right? -2/4. So your solutions should be x equals -1/2 plus or minus 1/2 radical 3. Or if you want to write that as radical 3 over 2, that would be fine as well. Okay. Remember, those are just the x values. Now, when we got x values of 5 and 7, it was so nice and lovely to plug them in and get the y values. It's a little messier here, isn't it? But it's all right, right? I mean, I could still distribute a 2 in there and kind of see what's happening for the y values and then subtract 3 from that. So what we're going to wind up doing is if I take this and I plug it into the linear function, because I think that will be easier. 2 times -1/2. We have to do plus radical 3 over 2 and then minus 3 at the end. So that's one of the roots plugged in for x in the linear function. So that's going to be -1 plus radical 3. If I distribute that 2 in, right? Minus this 3 over here. So one of the y values is -4 plus radical 3. It's the y value that goes with this value of x. If it's -1/2 minus radical 3 over 2, and then minus 3 afterwards, we're going to get -1 minus radical 3 minus 3. So you just get -4 minus radical 3 for the y value there. Okay, so all said and put together here, here's the solution. It's going to look weird, okay? When I tested -1/2 plus radical 3 over 2 as an x value, the y value was -4 plus radical 3. And the other solution was -1/2 minus radical 3 over 2, comma, -4 minus radical 3. The hardest part about this is probably in the end, even though, quadratic formula, okay, we got those two solutions for x. It's probably in the end when I plug them back in, simplifying and knowing that these are the y values that go with those corresponding x values. And just out of curiosity, let's see what those are as decimals. So -0.5 plus radical 3 over 2 is going to be 0.37-ish. And if I do the same thing with a minus in between, the other value of x is -1.37. Okay. For the y values, -4 plus radical 3. And then there's a reason why I'm doing this. I'm going to check it on my calculator. -2.27 and -4 minus the square root of 3 is -5.73. So what I'm going to do in a moment here is I'm going to check on my calculator that these are in fact the correct solutions. Now I want you to have, I like the way that exact form looks as opposed to those decimals I had to round. But if we go to y equals right now on the calculator and we go to, let me slide this down a little bit. I'm going to type the linear function in y1 and the quadratic in y2. I'm going to type them because we had them nicely solved for y equals from the start. So 2x minus 3 goes into y1, 2 times x plus 1 squared with a minus 6 goes into y2. I'm going to zoom 6 and graph this. See what we got? There's my linear function. Let's see the parabola come through. Okay, what I want to double check is, are these solutions correct? Is 0.37 comma -2, it looks like it's correct. Could I confirm by finding the point of intersection, second trace, calculate the intersect? Let's see, this point of intersection occurs at, hopefully you can see it on my screen, 0.37, -2.27. Look at us go. All right, is the other one in the correct location? Second trace, calc the intersect of this point right here. That's -1.37, -5.73. Perfect. So yeah, we can definitely check on these things graphically when we type into y1 and y2, Because if you get answers like this, you might be like, holy cow, is that even close to being correct? And then once you check on the calculator, you can confirm, yeah, those are actually the correct solutions. So in the end, they cross at these not so nice looking irrational points of intersection. But those are the solutions. Okay, I've got one more to do with you. You're going to like the last one, I promise. If you didn't like that one, you're going to like number 3. All right, so for number 3, let's take a look at y equals 3x minus 7 and y equals 2 times the quantity x plus 5 squared minus 4. Okay. The nice thing about this example, as compared to what we did in number 2, is that they both already say y equals. So we don't have to do any rearranging. If these both say y equals, you can actually just start right away by setting those equations equal in terms of x. So 2 times x plus 5 squared minus 4 is equal to 3x minus 7. And now we just got to do a lot of algebra to clean up. I'm going to go through this kind of quickly. Hopefully I don't make too many mistakes in that. So this becomes x squared plus 10x plus 25 when I expand that. So then from there, I'm going to distribute a 2 to make it a 2x squared plus 20x plus 50. Combining the like terms of 50 minus 4, we get 2x squared plus 20x plus a 46 there equals 3x minus 7. All right, move some stuff over to this side, subtract the 3x over to make it a 17x in the middle. And if I add 7, that's now plus 53 is equal to 0. So things that multiply to 53, I'm pretty sure 53 is prime. So I'm not thinking that I'm going to be able to work with the factors of 53 and 2 to somehow magically get 17 in the middle. So I guess we got to do quadratic formula. Okay, so we're going to do x equals negative b, which is negative 17, plus or minus the square root of b squared, 17 squared, minus 4 times 2 times 53, all over 2a, 2 times 4. Okay, so x equals 17 plus or minus, let's see what that number is under the radical here. So we got 17 squared, oops, not to the negative 1, let's try that again, 17 squared, minus 4 times a times c is negative 135 under the radical, and that's over 8. All right, the reason why I said you're going to like this one, because you probably haven't liked it up until this point. You probably think I'm a big liar. You're like, Mr. All, why don't these numbers are getting too large and we got negatives under the radical? Well, we know that when we take the square root of a negative, square root of -1 is I. So the solutions are some sort of imaginary solutions. So what does that mean about the solutions overall to this system of equations? If you solve for x and in the end, x has non-real solutions, right? These are imaginary. That means the system has no solution. Okay. And the reason why we know that is that when I tried to solve for x, I didn't get real answers. So there's no sense in plugging these in because the y values, it's going to be some imaginary component as well. So what does that mean graphically? It means that if you were to graph the line and the parabola, they just don't cross. Okay, and you can confirm that by going to y1 and y2 on the calculator. They just don't cross one another. So that's why I think you'll like this one, is that you got towards the end and you're like, oh boy, I'm going to have to plug these in. The answer is actually no, you don't have to plug them in. Imaginary roots imply that the system has no solution. All right, well, I lied a little bit. I'm not going to do this one with you, but I will give you a fourth one as a challenge to think about. Y equals x squared. So that doesn't seem too challenging, but what if I paired it with x squared plus y minus 2 squared is equal to 4? This is not a quadratic linear system anymore like the other three have been. This is a quadratic with a something else that maybe you know what it looks like. See if you can solve that system. And that's just kind of a challenger. You don't have to do it by tomorrow, but if you're interested and you're like, you know what, Mr. All, I'm up for the challenge, then you guys go for it, okay? All right, that's it for today's lesson on solving systems. More to come, and next time I see you, we'll talk about that challenger as well. Have a great rest of your day.